I'm Ted Weatherford, VP of Business Development at Xsight Labs, and my distinguished colleague.
Yep, John Carney. I'm a software architect on the E-Series, which is what we'll talk about.
And I'm just going to kick it off by saying the E-Series is a separate chip. It's a SoC, and we call it cloud on a chip because it's got all the elements of cloud. It's got the Ethernet connectivity. It's got security. Okay. It's got the virtualized storage. And of course, it's got the processing with the ARM cores, 64 Neoverse 2 ARM cores. It's in production in about 4 months, and it's been general available for 4 months. And these are just the different form factors you could get it in. Okay. We sell a server. We have one here to show you guys. And we also have the add-in card, and you can add it into the server. So the server has an add-in card slot or two in it. So we can put our own chip as a server and then a smart NIC together. And then we have the COMEX. And the COMEX is really targeting the control plane applications, but it's actually just a really nice embedded format that, well, you could have a 64 ARM core product on. John, take it away.
Yeah.
Thanks.
So the first thing I'm going to do is I'll talk about what the architectural differentiation is between our DPU and what traditionally has been the DPU offerings from our competitors. So the traditional DPU really started and evolved from a NIC. So what has happened in the past is the NIC would be taken, there would be some flexibility added within the pipeline of the NIC, and then to add even more flexibility, a CPU cluster was added to the NIC. And this is what our competitors' architectures look like as a DPU. And this architecture is constrained, and the reason why it's constrained is because the CPU cluster is not really sized, and the connectivity of the CPU cluster to the offload NIC is not sized so that all of the packets, all of the processing of the data plane could go to the ARM cores or go to the CPU cluster for processing. It really relies on being able to process most of the packets in the hardware pipeline, and only exception packets, or maybe the first packet of a flow goes to the CPU cluster. And what we found with this architecture is that for many workloads, there's flexibility that you need that doesn't exist in that hardware pipeline. And you often are trying to get all of the packets to that CPU cluster, and then your performance is limited. What we did differently is we started from that CPU cluster and we said, let's take a very energy efficient and optimized for data plane applications, server class compute system, and let's size it so that all of the packets, and in fact, all of the PCIe transactions when you're attached to a host can all be terminated and processed in software using standard programming models, not proprietary programming, but just a standard Linux or user space programming. And so that's what we started with. And then we added to that an Ethernet unit, which provides the Ethernet connectivity and provides some processing that's done on sort of the throughput or the bits of the packet, like encryption. And then we added a P unit, which is the PCIe connectivity, which when you connect to a host or you can connect devices to the DPU, they go through the P unit. But again, all of the data plane processing can be done in the cores and not in this model on the left where you really have to do most of your processing in the NIC portion of this architecture. This on the right allows us scalable performance. We can scale performance with cores. And again, it's a very standard development model. And I think we can go to the next slide.
Yeah. The competition does it differently. They start at the offload NIC and they add ARM cores. And they traditionally, for 3 generations, haven't added enough ARM cores and haven't added the more powerful ARM cores like the Neoverse 2s.
Yeah.
So, and we're really vindicated that with the Bluefield, right? The Bluefield's come out and said 64 cores, and it's come out and said, okay, let's put a real compute in there. So we see them as our principal competition. The Intels and the Pensando AMDs are still kind of sticking to their guns with the other approach.
And your programming model on that solution is Linux?
Yeah, so we run Linux, we run, and we'll get into this more in some of the other slides, but we run Linux. We will be certified as an ARM system ready. Actually, we're certified as a server class, not an embedded class, meaning that any operating system distribution that can run on an ARM server can run on our DPU. And so we see, and we'll get into use cases as well, but we see use cases where customers want to do everything in the Linux kernel, all of the, networking stack of the Linux kernel. And we see a lot of use cases where customers want to use user space frameworks like DPDK or SPDK and do all of the data plane programming in user space. One of the big advantages that we have is that a lot of these data planes already exist. The customers have been running them on servers. And now what they can do is they can take those data planes that they're already running today on servers, and they can retarget them unmodified onto the DPU, and they get a huge gain in performance per watt, in density, to be able to put multiple of these E1s in a small form factor. And so that's really an advantage we have, is that all of those existing data planes that people have run on servers can just be placed onto the E1.
Sorry,
Sorry.
go ahead.
Go ahead, Jack. I'm sorry.
I was just going to ask, so on the traditional side, it's all custom code, right?
Yeah, so it's a combination, and the combination is what actually makes it difficult, because there's sort of custom code that runs in that offload NIC portion of it. It's usually proprietary. It's usually very resource constrained. And then there may be more sort of standard programming model on the CPU cluster. But to create an application, you kind of have to split the application between these two very different programming models.
Mm-hmm.
And that's what makes that that environment very difficult to program. Yeah.
I think it was also a problem in the security hardware market too, right? When I've got to do packet processing between the CPU and my offloading NIC, right? It's a huge issue, because
Right.
I've got to have almost a one core application to do that kind of processing. So if I can put it closer, then it makes a lot of sense.
Right.
So in that case, then, because you're traditional Linux based, you can run into Linux things. So are people doing eBPF on this?
Yep, you can run eBPF. So we see that there's a camp that's sort of the Linux eBPF. There's another camp that's the user space DPDK.
Okay.
And we support both, and I think we'll show that a little bit more in some of the future slides. So it's really, again, it's just, if you've programmed data planes on a server, this is just a very familiar environment to you. Okay, I think we can go to the next slide. So this is a closer look at the actual chip architecture. So in the heart of the architecture is that compute fabric. That's where our 64 ARM Neoverse N2 cores are. They're connected with a high-speed, scalable, cache-coherent fabric. We support 32 megabytes of system-level cache that's shared by all of the cores. The cores also have their own private L1 and L2 caches. We have a memory subsystem where we have 4 channels of DDR5 memory. Those can operate up to 5200. This is a little bit unique. Most DPUs don't have that much memory I/O. And depending on the form factor, Ted showed those form factors earlier. In some form factors where you're not as space constrained, you can populate all 4 of those memory channels. In some other form factors where you may be more space constrained, you might only populate 2 of those memory channels. But we give you that ability to use more memory I/O depending on your use case. A very unique aspect of this chip is our PCIe connectivity. So we have PCIe connectivity that could be host attached, where you connect the DPU to a host. That's a traditional kind of DPU application where we're acting as a NIC to a host. We did something unique where we, in hardware, created PCIe hardware that presents all of the services of PCIe to the software so that the software can emulate any kind of PCIe device. So to a host, we can look like a storage device, we can look like a networking device, we can look like an RDMA fabric device, and it's all software defined, again, using just standard programming models. We support up to 40 lanes of PCIe Gen 5. Some of those lanes are typically used for, like an NVMe boot or peripherals, but then there's 32 lanes which would typically be used in your data path. That data path can allow up to 800 gig of PCIe bandwidth towards a host or towards storage. We'll talk more about storage later, or towards other devices. On the bottom of the diagram, we show our Ethernet, or we call it a E-unit. And this appears to the programmer as your NIC. It appears like a NIC. It appears sort of like an enterprise class NIC with the features that you would expect in a NIC. It also has several offloads. We support inline encryption. We have a lot of flexibility in what kind of formats we can support. It also supports all of the normal stateless offloads that you would find in a NIC, things like CRCs and checksums. It also supports lookups, and you can do some flow offloads in the NIC portion of this chip. And the way we think about it, and the way our philosophy is that Ethernet hardware is really there to help steer traffic to the cores, to enable you to scale the processing of those packets on the cores. So we're not trying to do all of the processing and all of the flexibility in the NIC portion like our competitors are. We're trying to do the primitive operations that you need there to enable you to use those ARM cores effectively. A little bit on power. So the chip itself, typical use cases would be, for typical would be 50 to 75 watts. And, for thermal design power, it's up to 120 watts. This is rated with a spec int of 170, which is a significant amount of compute power in such a energy efficient chip.
And John, Jack Pollard with Paradigm Technica. I noticed that you have a memory encryption block in front of the memory.
Yeah.
Do you support, so is it, you can support secure encryption data in use?
So we have like multiple different places where we do encryption in this chip, and I'll talk about them. So one of them is inline, as data comes in and out of the Ethernet interface. And so that's like your IPsec, or Google has something called PSP. Also, Ultra Ethernet has their own security. So all of those can be done inline. And if you can do them inline, that's really the best place to do it, because it doesn't require you to bounce the data through your memory system multiple times.
Sorry about that.
We also have a look-aside crypto engine. And so there's things like TLS, TLS, where you want to terminate like TCP traffic that has TLS. And it's very stateful, and it's not something that's easily done in line. So we have a look-aside engine where the ARM cores can kind of feed that look-aside crypto engine and do encryption there. Then we have the memory encryption. The memory encryption is really there so that data that's stored in the DRAMs on the chip can actually be encrypted.
Okay.
So that there's not any way you can kind of snoop on those memory interfaces and be able to, access any kind of sensitive data. It also ultimately can allow you to have multiple tenants sharing, cores on this chip, and be able to isolate, their data in a way where they're each encrypted from each other.
That's sort of where I was going. I was wondering if you could do a secure enclave in this.
Yeah, so I'm not really the right person to like get into the details of that. We have security architects that could really answer all of that. Yeah.
A quick question on your PCIe side. Is that capable of doing CXL interfaces as well?
So we did not implement CXL in this chip. We're not going to really talk about roadmap too much for this chip, but that's something that is very much in mind for us on our roadmap.
Okay, because I mean, there is some interest in the industry in the ability to actually have essentially NIC to CXL
Yeah.
interfaces.
Yeah, and this is something that we're following closely again, and
Seeing that. We're
Yeah,
seeing that.
yeah,
Yeah.
yeah,
Memory
yeah.
for sure.
This chip does not support CXL, but stay tuned.
Yeah, the follow-on's called the E2. We don't have a roadmap slide
Yeah,
on it, but yeah, sorry. Yeah, sorry. Yeah, the follow-on product is the E2, and it's roughly double the bandwidth of this one. So it'll be a 1.6T-ish type product, above 1.6T or 1.6T, and that's where you'll see the CXL support come in.
Okay, I think we can go to
Yeah,
the next slide.
Sure.
So we'll talk about some of the applications. Starting from this server class kind of architecture, you can imagine that there's a very broad set of use cases, and we'll talk about some of them. We'll talk about the ones that we've really been focused on. This chip was really architected for this use case on the left. We'll call it the front end DPU. And this use case can either be just a traditional public cloud compute node. In that node, the tenants need to get access to the infrastructure. The DPU is what provides the virtualization of the infrastructure, the securing of the infrastructure, and for both networking and storage. And it provides isolation amongst the tenants that are running on the host. But the front end also applies to an AI cluster where essentially the same kinds of things have to be done for the AI cluster to provide access to the infrastructure, access to the storage. And in the for the AI use case and both for the traditional cloud compute use case, the DPU is really offloading the host and offloading the DPUs from having to do those functions, and offloading it in a way where it's done on a very optimized architecture for those workloads that are running on the DPU. The backend DPU, so typically in the sort of training clusters, these high scale training clusters, this backend NIC function has traditionally and predominantly been done with the performance NICs. Those NICs allow you to get, RDMA performance at very high rates and low power. And there are opportunities in those large clusters for DPUs more around innovating around congestion control or congestion avoidance, packet spraying, telemetry. There are many use cases where even in a training cluster, the DPU makes sense. But really in the inference cluster is where the DPU can shine because in the inference cluster, that's where we start to see the offload of KV cache offload from the GPU to something else. And the DPU is a natural place to do that because it has direct access to the GPU's memory system, but it's also directly connected to the scale out network of those inference clusters. So as we see a push to building special purpose clusters for inference, there's a lot more opportunity for the DPU in those. We also have use cases for local storage. And in the local storage use cases to the host, we can virtualize storage devices, but those can actually be, the E1 and the DPU can actually be managing a local set of disks. There's a bump in the wire use case, and this is one diagram. There's many ways to draw this bump in the wire, but you can think of the bump in the wire as just simply a network attached appliance where packets come in, maybe come in on one port, get processed, go out another port. Many applications for bump in the wire, both in security, in software load balancing, and we see many use cases there. Smart switch is another use case that I think we'll touch on more later, where we actually combine the switch with the DPUs. What this allows is it allows you to use the switch to have a large bandwidth of traffic coming into the switch, and to selectively choose which flows you want to go to the DPU for more processing. Typically, the switch is doing your stateless processing, and the DPU could do very stateful processing. I think we can go to the next slide, Ted. And then we have server use cases. So we have edge server use cases. We see a lot of applicability for DPUs for things like CDN. For gaming, we see use cases. And then on the right, we see the E1 in sort of an appliance form factor for storage target kinds of use cases where the storage is disaggregated from the host. This is sort of a look at our software developer kit. I've said multiple times, I think so far, that we're standard programming model, but we do provide software in a few forms. We provide the drivers and the necessary infrastructure pieces of software to enable our customers to use the DPU. And we also provide reference software for many of these applications and use cases. So at the lowest level, we provide the secure boot, the BIOS, and the sort of low-level software that gets the chip booted and operating. And then as far as the operating system, as I said earlier, any operating system distribution that can run on an ARM server can run on the E1. Internally, we've been using Ubuntu. That's kind of our sort of default. And then we provide the DPDK Linux drivers on top of that for our networking. And then as I talked about the PCIe, where we can emulate any kind of PCIe device, we implement what we call backends. So we implement a backend for networking. We have a couple flavors of that, VirtIO and XNA. We implement a backend for NVMe emulation, and as well as backends for RDMA and Rocky. And then as you go above that, you start to get into the applications. And typically, our customers will use our chip as a platform, and then they'll put their own applications on top of the E1. There is an application that we've developed called Sonic Dash. We'll talk about that more in a couple of slides. And that's where we'll really get into some of the performance in a real world use case, SDN use case for the E1. Okay. Right now. So the reason why we kind of selected Sonic Dash to talk about is because this is a very heavy workload, SDN workload. And so what is Sonic Dash? Sonic Dash is a Linux Foundation project that was started in 2021. It was really a project pushed by Microsoft. And the goal of the project was to take the stateful services that run on the host in the public cloud and define them and define the APIs and the object models in those services. And the goal of that was to enable a broad set of technology providers to really create performance and power and cost optimized implementations of these services. Traditionally, that cloud SDN had been built on frameworks that had primitive operations, and a service was sort of defined as stringing these primitive operations together in order to implement the service. And over time, as the cloud matured, it got to the point where we no longer need this kind of low-level way of defining the services in the cloud, that we could do it by actually, we know now, after decades of cloud computing, that these are the 7 services, SDN services, that you need in the cloud. So they've been defined, and we've been implementing them. One of the services is called VNet to VNet. What does this do? So packets come in, you apply lookups, transformations to be able to map the overlay to the underlay, does state tracking for TCP and UDP connections. Dash defines that you have to do 5 ACL operations. ACL, algorithmic ACL, is a very intensive, especially at high scale on memory accesses. Accounting, enforcement of rate limits, flow scale limits, and also you need very high availability, because if you're tracking millions of connections, you need to make sure that that state is synchronized on another data plane. So if there's any kind of failure in the network, all of that traffic can be taken over by a peer data plane, and so there's no loss of connections to the users of the network. In order to run Sonic Dash at an 800 gig scale, it requires millions of routes, millions of prefixes in your ACL tables, millions of mappings. The point of showing this scale is that this kind of scale is not something that you can fit on chip memory. All of this has to live in DRAM off of the chip. And there's also no locality. As packets come into the chip, a packet might be for one flow, next packet's for a different flow, and you can't rely on those caches for locality. Everything has to go to DRAM in order to be able to process the packets for Sonic Dash. It doesn't matter what architecture you have. It doesn't matter if you have like the E architecture or one of our competitor architectures. It's a very DRAM intensive use case. So if we go to the next slide, we can show that there's a test defined for Dash called the Hero benchmark. It's the highest scale, most intensive test that you can do. The test requires that you have over 120 million background connections. So this background traffic is running. And then while that background traffic is running, you have to be able to support 12 million new connections per second. And you have to be able to do that for 100 seconds without a single packet drop. We, on the E1, have been able to exceed that performance. We were able to get almost 20% excess on that performance requirement. We're able to do it where we still have cores left over, so you can run those remaining cores for your Sonic control plane. And even with the performance we were able to achieve, we still see the potential to achieve even more performance gain or be able to do it with fewer cores. And we see like the potential for another 25 to 40% performance improvement over what we've already tested. So this is just to give you an example of a cloud SDN use case. It's really the use case that we designed and architected the chip for, and to show that we're actually the only DPU that's able to pass this test at 800 gig with a single device.